Hello everyone, and welcome to tonight's stream, and we are continuing from where we left off. This is now 3.5. Usual rules apply. This is Book of Proof, 3rd edition by Richard Hammock. The download is in the description, so get the book. It's a very nice book, and I have a physical copy, and the physical copy is also really nice. Anyway, the book is in the Creative Commons, so feel free to download it. The answers are in the back of the book, so I do the reading, and then I do the questions. I do the odds only, so we don't damage the integrity of the book as a teaching resource. And you can actually know whether I'm getting the answer right or wrong before I do. So by checking the back of the book or following along. We are at page 85 now. Okay. The previous section dealt with counting lists made by selecting k entries from a set of n elements. So far, this is what we've been doing. Okay, we turn to a related question. How many subsets can be made by selecting k elements from a set with n elements? Okay, to see the difference between the two problems, take A. Right. So this set consists of these elements, these 5 elements, A, B, C, D, E. Consider the non-repetitive lists made from selecting 2 elements from A, which, so we're going to say P 5, 2. And remember, the notation is P and K. And to tell how many that is, we can also use this over. So that's n factorial over n minus k factorial. And of course, that comes out to 5 factorial over 3 factorial, which is equivalent to 2 factorial. And let's see, wait a minute. Yeah. No, not 2 factorial. That's wrong. Which is equal to 5 times 4 times 3 factorial over 3 factorial. Those two get scratched, which is equal to 20. And yeah. So 20 lists can be made. Remember, so what it's saying is that because it's k entries, that means that we're just going to have sets of 2. So it'll be like A, B, and then comma, we can have, actually, see, let's actually write out how they're doing it here. A, B, A, C, A, D, etc. Okay, so, but there are only 10 two-element subsets of A. And the subsets of A, now this is the, this goes back to what we did previously in previous things. If we were to do how many subsets can we make of 2 items. So in other words, the subsets, so the first one is an element. This is an element. Elements, this is subsets. So remember, we have to use, whenever we do elements, we use parentheses. For subsets, we use curly braces, or for sets. So that's set notation there. So we have A, B. Wait a minute. AC, comma, AD, okay, and so forth. So, now there's only 10 of those. The reason there are more lists than subset is that changing the order of the entries of a list produces a different list. But changing the order of elements of a set does not change the set. So, in other words, okay. When we have a subset, these items are interchangeable, and it would still, you can do that. And here, you can't do that. In other words, if you interchange this, this is let me draw this a little bit more clear way. Okay. Inside here is a box, and the two items, A and B, they're floating in the box. It doesn't matter if you list BA or AB, you could shake the box all you want. Now the element list AB is not equal to BA. Alright, so that's something else now. And so yeah, that's important. This section is concerned with counting subsets, not lists. As noted above, the basic question is, how many subsets can be made by choosing k elements from an n-element list? We begin with some notation that gives a name to the answer this question. Okay, so this is going to be here. If n and k are integers, so we're going to use this kind of notation. N, k notation, okay? And it's the number of subsets to be made by choosing k elements from an n-element list. Okay. So then we have, it's called n choose k. Okay. So this is called n choose k. Now, this is right here. This formula is k permutation, by the way. This one right there. So the n choose k, the way we're going to do this is that it could also be written as this. C choose n like that. You can also do that. Here we go. Now we're going to look at some examples here. Okay. Okay. All right. So we have, that's our set A, B, C, and D. Now, if k is -1, and then we're going to say our, let's see here, so we have 4 minus 1. So our n is 4. It's going to remain 4. But we're going to say k is -1. Then the answer is 0. Well, this is equal to 0 then. We can't have any -1 elements. It doesn't work. Like, what would be a negative subset? What we can have is a 0 subset. Now, the 0, of course, is the empty set. So, for 0, we could always have the empty set, which is subsets of 1. Okay? And this is our subset right there. Or the empty set. Right. Those refer to the empty set. Now we have here, how many singleton subsets can we have? It's 4 choose 1. And then we can have 4, A, B, C, and D. So 4 is the answer here. And then, we have curly braces 1. Actually, in this, it's not 1. It's A, B, C, D. Okay. What about doubletons? How many can we have? So we're going to say 4, choose 2. Okay. So it's going to be AB, AC, AD. We can have a total of 6 here. And I guess I could list all of these here. We're going to say A, B, A, C, A, D. I'm going to say B, C, B, D, and C, D. 6 doubletons. And then we're going to say here, okay, we're going to say 3. About tripletons, how many can we do of those? So previously I talked about whenever you have a situation of 4 of them, then and you want to do tripletons, you could always have 4. We talked this in chapter 1. It's going to be, so an easy way to remember it, it's ABC, and then ABD, and then I'll show you real quick. So this is the one where if you're ever doing these subsets, then this is the one where you often make a mistake and you forget one of the tripletons. But on a set of 4 items or elements, you can get 4. So let's do that real quick. So we're going to say A, B, C, A, B, D, and then we're going to say ABC, and then A, B, D, A, C, D. That's the one that's usually, it's 1, 3, 4 is the one that's usually missed. And B, C, D. So 1, 2, 3, 1, 2, 4, and 1, 3, 4 is usually the one that's missed because 2, 3, 4 is easier to remember. If you are ever stuck and you have a 4-element list and you could only think of 3 of them, that's 1, 3, 4 is usually the missing one. Anyway, just from my own experience. So yeah, this is going to be 4, choose 3, and there's 4 of them. Okay, and then we're choosing 4, and of course that's just a set. A, B, C, D, and then it's 4, choose 4 is equal to 1. Going overboard, 4, choose 5 is 0 because we can't have it bigger than the list itself. So yeah, it doesn't work that way. In this case, you would have to add additional elements. Yeah, when we create subsets, you stop at the full set. You can't go overflow the full set, basically. Okay, so that was page 85. Continuing on. The values of k appear in the far left column of the table. To the right, okay, let's see, I'm just going to read. I think they're just going over everything we just did. Okay, yeah. In general. Okay, yeah, they're just explaining everything we just did. Trying to get to where the next step. Notice that if k is negative or greater than the cardinality of A, then A has no subsets of cardinality k. So 4 choose k would be equal to 0 in those cases. Basically what I just went over. In general, n choose k equal to 0 whenever k is less than 0 or k is greater than n. So in other words, if whenever you have a negative k, or a k that's bigger than the amount of elements in the set, then you're going to end up in 0. I'm really concerned about the word in general here, though. I mean, there's some kind of condition where that doesn't hold, and I want to know what that is. But for our purposes, it's nothing we have to worry about. I mean, this is pretty standard. In particular, this means that, basically just want to, although it is not hard to work out the values of 4 choose k by writing out the subsets in the above table, this method of actual listing sets would not be practical for computing n choose k when n and k are large. We need a formula. To find one, we will now carefully work out the value of 3 choose 5 in a way that highlights a pattern that points to the formula of n choose k. To begin with, note that 5 choose 3 is a number of 3 element subsets of A, B, C, D, E. And we have a table for that. And we see that 5 choose 3 is equal to 10. So, okay, continue. The column under, you have to look at page 86 basically, but I'm going to read and try to go explain how this works. The column under each subset tallies to 3 factorial, which is equal to 6 permutations of that subset. The first subset, ABC, has 3 factorial permutations, right, which is equal to 6. They're listed below it. The second column tallies permutations of A, B, D, and so on. Okay, so right, there's the 3 factorial. So the table consists of, the body of the table has 5 choose 3 columns, and it has 3 factorial rows. So in other words, it has 3 factorial rows. So it has 6 rows, correct, and it has 5 choose 3 columns. All right, and then so it has a total of 3 factorial times 5 choose 3 lists. But notice that although the table consists of every 3 permutation of A, B, C, D, E, fact 3.4 says that there are P5 choose 3, which is equal to the formula we had before, which K permutation formula, which is 5 factorial over 5 minus 3 factorial, so 3 permutations. Thus, the total number of lists in the table can be written as either 3 factorial times 5 choose 3, or 5 factorial over 5 minus 3 factorial, which is to say that 3 factorial over 5 minus 5 choose 3 is the same thing, dividing, okay. So basically, this is what they're trying to say here is that n choose k, there's the k permutation formula, which is, this is the formula here. Okay. So n choose k, if we wanted to find out what is the number of subsets of any given thing, we're going to say we're going to have n factorial over k factorial times n minus k factorial. All right. So this is the thing that we're going to be using. Okay. So basically, that's going to tell us, remember, k is the size of the subset, and n is the number of elements in the set. So basically, we have, let's say, A, B, C, D. We have 4n, and we want to know how many subsets. So let's actually use this formula off of what we already have done here, right? Okay, so let's start with, let's start with one that's going to be positive. So we're going to say, actually, no, let's just test it on the negative one. Okay, so using the first one right here, and by the way, n for all of these is 4, as we know right here. Okay, so let's do that. So we're going to say 4 factorial over negative 1 Actually, I don't even know how negative 1 factorial is going to work. Can you do a negative factorial? I don't even, that doesn't make any sense. However, okay, we're going to skip the negative 1 right now. Let's just stick to, because as a rule, we're gonna take it on faith that any negative k will result in 0, regardless of the size of the negative k. So, because what is it a negative subset? It doesn't even really make sense. But we're taking on faith for now. Instead, what we're gonna do is we're gonna start with k equals 0. So let's do that. So we're gonna go with 4 factorial over k is 0 factorial times, we have 4 minus, we chose k as 0, 0. We have factorial. All right, so that becomes 4 factorial over 1 times 4 factorial, which is equal to 1. Because the factorials cancel. All right, cool. So that works. So that way we know that, let's repeat it again. We know that we can have, if we were to just go with 0 element subsets, there are no elements, not A, B, C, or D, none of it, we can still get 1, and that's the empty set. So that works. So yeah, right there. Now let's make k be 1 now. What happens? So we're going to say n factorial over k factorial times n minus k factorial. Okay. Well, in that case, we get 4 factorial over... Now, the 1 factorial is just 1 times 3 factorial, which is equal to 4. Because it's going to be 4 times 3 factorial over 3 factorial. And the factorials cancel. So that's correct. So now, we can have 4 single element subsets of our set. And those are the singletons. So that works. All right, let's keep trying this thing. Okay, so let's see, what about 2? Okay, we're going to go n factorial over k factorial minus n minus k factorial. What do we get then? So then we have 4 factorial over 2 factorial over 2 factorial, which is going to be 4 times 3 times 2 factorial over 2 factorial, 2 factorial. We're going to scratch one of those factorials. So that's going to be 12 over 2, which is 6. That works. Okay, so far so good. All right, well, in that case, let's do, now we're doing 3. So we're going to go 4 factorial, so n factorial over k factorial, and then n minus k factorial. All right, so then we have 4 factorial. Actually, you know what? Let's simplify that right away. I'm going to say 4 times 3 factorial over 3 factorial times 1 factorial, and that is 4. That works. All right. And finally, we're going to go with 4. All right, so n factorial over k factorial with n minus k factorial. So then we get factorials cancel. We have 1 over 0 factorial, which is 1 over 1, which is 1. Okay. What do you know? It all works. Cool. Alrighty. Well, that's going to be a great formula. Now, I hope you understand how that works now. If you don't, you have to just keep trying this thing over and over and try to understand this. Go over the section because it you have to drill this portion into your head, and you also have to, like, the past 3 chapters are incredibly important, especially for combinatorics and things like that. This formula is very, very, very important. So you have to understand what n choose k means. What are the k elements? What is the n? What we're trying to do here? We're counting the number of subsets with this formula, but we could also, like, I don't want to confuse between the 2 chapters, but in my opinion, this and the previous chapter are some of the most important chapters so far in this book. I mean, granted, every chapter is incredibly important, but like in terms of things that I had to do in the graduate level course that I passed, it's ironic that I passed a graduate level course, but not this course. Long story. But basically, yeah, there was a lot of things that, you know, where, and by the way, I still have the book. I mean, I keep all my math books and I keep all my textbooks in general, but yeah, I'm gonna drill that combinatorics book after I finish this one. Now, it's not open source, so I'm not gonna be streaming it, but what I'm saying is the material here is incredibly important. Anyway, let's continue on. All right, so that kind of worked out. Okay, so yeah, we just ran through a bunch of examples. I'm trying to figure out where to pick it up now. Okay. Right. So, as a final note, but this is page 87, fact 3.5. I'm just gonna start it on a new page now. If k is greater than 0, but greater than or equal to 0, or less than or equal to n, then n choose k is equal to our formula. N factorial over k factorial times n minus k factorial. And we're going to say otherwise n choose k equals 0. Okay, so that's just a fact, and we're sticking to it. See, this is the part that I'm trying to understand. If this is the fact, then why did they use the word in general? I don't know, maybe they were talking about different kind of numbers or something like that. I guess this applies to integers. Yeah, because how would you do a half a subset, right? What is a fraction of an element? That doesn't make sense. Okay, so let's continue on. Let's now use our knowledge to work on some exercises. How many size 4 subsets does this set have? Size 4. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's just be clear. This has has 9 elements. N equals to 9. Okay. And then we want to know how many subsets, size 4. I'm going to say how many size 4 sets. So we're going to assign K to 4. Size 4 subset, remember, is something like this. We're going to say 1, 2, 3, 4, or it can be 4, 6, 8, 9. Those are examples, right? Okay, so we're going to use our formula. Let's do it. We're going to say n factorial over k factorial with n minus k factorial. All right, let's do that. So then we got 9 factorial over 4 factorial times 5 factorial. So let's split up the 9. We're going to say 9 times 8 times 7 times 6 times 5 factorial over 4 factorial times 5 factorial. We're scratching the 5 factorials. So now we have 9 times 8 times 7 times 6 over 4 factorial. All right, so that's 3024 over 4 factorial. So that's over 24. Which comes out to 126. All right, yes, okay. Good. How many 5-element subsets of A? Wait a minute. No, hang on. Let me read this one more time. Question 2. How many 5-element subsets of A have exactly 2 even elements? Okay, so then have exactly 2 even elements. All right. Well, we have our sets. So now we're saying, let's write the question here. How many 2 even, how many 5-element, 5 have 2 even elements. Okay, so so the K is going to be equal to 5. Now the N is going to be different. So we have to think about this for a minute here. I'm going to read what they're saying here. Okay. Making a 5-element subset of A with exactly 2 even elements is a 2-step process. First, select 2 of the 4 even elements from A. Select 2 of the 4 even elements from A. So, all right, we just need 2 of them, and right. So then now what we're doing is there are a total of 4 elements in A, right? 2, 4, 6, and 8. So we're going to say 4, and we're going to say we want 2 of them. All right, because our sets are going to be like this. So we're saying 4, choose 2, and let's see how that works. So now this is we have a new n assigned. Where this is a 2-step process, like I said earlier. So it's 4 choose 2, so 4 factorial over 2 factorial times 4 minus 2 factorial. So that comes out to, we have 4 factorial over 2 factorial over 2 factorial, which is 4 times 3 times 2 factorial times 2 factorial times 2 factorial. There we go. So that becomes 6. All right. So there's 6 ways to do that. Okay, good. Now, I'm going to take out part of this because I'm going to need some room here. Okay, let's see here. So we have 6 ways to do that. Okay. Now, the next question becomes, continuing on. There are 5 choose 3 to select 3 of the 5 odd elements of A. So basically, we're trying to figure out how many ways can we get different mixes. So this is a partial mix, right? There's going to be 2 evens and 3 odds. So just as we determined, we're only going to get 2 evens, but we don't know which 2 evens of the 4. And we know that we're going to get 3 odds because we're getting a bag of 5. But we don't know which of the 5, which 3 odds of the 5 we're getting. So we're going to say now 5 choose 3 to figure out the odd half of it. 5 choose 3. So that's going to be 5 factorial over 3 factorial with 5 minus 3 factorial. All right, and that comes out to 5 times 4 times 3 factorial over 3 factorial times 2 factorial. Scratch the 3 factorials, which is equal to 20 over 2, which is equal to 10. Okay, so now we have, there's 10 different ways we can get 3 different odd numbers of our 5 bag. And there's 6 different ways we can get 2 even numbers of our 4 even numbers. And now we just have to combine the 2 and figure out all the different ways they can mix. That we get 2 evens and 3 odds. Okay. And to do that, we're just going to multiply it. So at this point, we know we have 6 different ways to do one thing and 10 different ways to do another thing. What's all the different ways we can do it? It's going to be 10 times 6, 60. All right. Yeah. There's 60 ways to get 5-element subsets that have 2 even elements of our set that we have here, right here. Okay, well that was cool. All right, let's continue on. Okay. A single 5-card hand is dealt from a 52-card deck. Okay, 52-card deck. 1, 2, 3, 4, 5. We have 5 cards. Okay, 5-card hand. Okay, good. Then we have, how many different 5-card hands are possible? All right. So basically, our N is going to be 52. And see here. And then we're going to say our K is going to be 5. So it's going to be 52, choose 5. All right. So that's going to be 52 factorial over 5 factorial times 52 minus 5 factorial. All right, and that comes out to 52 factorial over 5 factorial times 47 factorial. Okay, so now we're going to expand this out a little bit. 52 times 51 times 50 times 49 times 48 times 47 factorial over 5 factorial times 47 factorial. Scratch our 47 factorials. Now we have 52 times 51 times 50 times 49 times 48 over 5 factorial. And 5 factorial, actually, I'm just gonna give it to you. It's 120. That's an easy one to remember. The first couple ones are relatively easy to remember. Just memorize like the first 5 factorials or something, and then just have it in the back of your head. Okay, so we have 52 times 51 times 50 times 49 times 48. Here we go. All right. 5, 9, 8, 9, 6, 0, 2, 5, 9, 9, 6, 0. Okay, there we go. And that is the answer. There's 2.5 million ways, almost 2.6, I'd say 2.6 million ways that you can get a 5-card hand and a 52-card deck. It's pretty wild. That is wild if you think about it. Yeah, it's pretty interesting. Okay. All right. Continuing on to the next page, we are on page 88. Example 3.14, pi. This problem concerns 5-card hands that can be dealt off of a 52-card deck. How many such hands are there in which 2 cards are clubs and 3 are hearts? Okay. All right, so we have, let's try this. We have 5-card hand, and then we have 52-card deck, and then we're gonna say and then club, and then 3 hearts, right? So you know what? Let's just draw it. K, comma, heart. Okay, so that is our hand. That's what we want. Okay. How many ways can we do that? All right. Well, what we know is there are 13 hearts, and we know there are 13 clubs. Okay, and now, so how many different ways can we get just hearts? Of the 13, how many ways can we get just 2 of them, right? Well, we're gonna say we can do 13 choose 2. And for the hearts, we're going to say 13 choose 3. All right. So we're going to say n factorial, and that's going to be 13 factorial over k factorial, 2 factorial, with 13 minus 2 factorial. And that's going to be the first formula. And then we're going to solve that. And then we're going to do the hearts. Okay. So that gives us 13 factorial over 2 factorial and minus 11 factorial, which is equal to 13 times 12 times 11 factorial over 2 factorial times 11 factorial. Scratch the 11s. We have 13 times 12 over 2 factorial, which is 2. Okay, so 13 times 12, 156 over 2. All right, so that's 78. 78 different ways we can get to. Now, if we're going to say 3, we have 13 factorial over 3 now, 3 factorial, with 13 minus 3 factorial. All right, so that gives us 13 factorial over 3 factorial and over 10 factorial. And then we're going to write 13 times 12 times 11 times 10 factorial over 3 factorial times 10 factorial. Scratch factorials. We have 13 times 12 times 11 over 6. All right, let's do that. That's 1716 divided by 6. That's 286. All right, and then we multiply that by 78. All right, and then we just take our 278 times 286, and that comes out to 22,308. Okay, cool. So yeah, basically that's how we can do it. And you can also write it like this. You can go like this. Just 13.2, 13.3. You can go like that. And then you can write them like this. We have 13 factorial over 2 factorial. 11 factorial times 13 factorial. 3 factorial, 10 factorial. So like, you can do it like that and then multiply it out. It's still going to be the same thing. But yeah, it was easier to go one than the other and then multiply the two. But that's basically the equation. All right. All right, now example 3.15. A lottery features a bucket of 36 balls. All right, and then we have 1 through 36. Okay. 6 balls drawn. Randomly. For $1, you buy a ticket with 6 blanks. You fill in the blanks with 6 different numbers between 1 and 36. You win 1 million if you choose the same numbers that are drawn regardless of order. What are your chances of winning? Okay. So let's think about this for a minute here. Okay. So let me read it one more time here. All right. So here we go. All right. Well, in that case, it's going to be 36, choose 6. Choose 6. Okay. Now, let me see here. I'm just reading the solution here as well. In filling out the ticket, you're choosing 6 numbers from a set of 36 numbers. So now when they said the order here, this is the part that kind of threw me off. Regardless of order, that same thing. We don't care about the order in the sense that as long as we pull the right number, the order could appear. It's just like with the cards. We're saying we wanted our 2 individual cards, so it could be like, say, like, I don't know, like 2 of hearts and 5 of hearts and 10 of hearts, right? But which order they're drawn in, we don't really care about that as long as we're getting those 3 in that set. So in that sense, it's fine. There's no impact there. We're still trying to get 36 balls and 6 are drawn. So it's going to be, here we go. N is equal to 36. K is equal to 6. Okay, so we have, and choose K. All right, so we have 36 factorial over 6 factorial, with 36 minus 6 factorial comes out to, we have 36 factorial over 6 factorial times 30 factorial. So that comes out to 36 times 35 times 34 times 33 times 32 times 31 times 30 factorial over 6 factorial times 30 factorial. We scratch that. Okay, and 6 factorial is 720. Okay, so yeah, so we have, let's multiply it out. 36 times 35 times 34 times 33 times 32 is 31. All right. Divided by 720. Okay. All right, and the answer is going to be 947792. There we go. Almost 2 million. 1 and 2 million, or basically, there's 2 million different ways that you can get a 6-number combination out of 36 numbers, which is pretty crazy if you think about it. And this is why the lottery is called the poor people tax. It's because your chance of winning is astronomical. Like, if you take that same amount of money that you would want to play in a lottery and you just put it in a stock, and even if it's an absolutely terrible pick, stocks generally tend to go up. Now, I'm not making any kind of investment advice. It's just simply as a statistical exercise here. Generally speaking, you would get like at least some possible return, or at least less chance of a loss, right? Like, you can play lottery and just like pretty much never win, or but yeah, it's once you understand statistics, lottery is just such. I mean, like, people think, oh, hey, the person down the street or the gas station attendant won, why not me, right? And if you don't play, you can't win, right? I mean, all that's true, but it's next to impossible. Best to think of it as it's impossible to win. Just saying. Just do the numbers on it. And of course, it's like it takes away the money, and you're not really, it's not a good investment of any kind. Okay, playing the lottery is never a good investment. There's this one guy, I forget his name, but basically he won lottery. He was winning millions, but the way he was winning millions, he was dropping tens of millions on tickets, which is absolutely nuts. So yeah, he had a huge problem, and eventually, you'd have to do some Googling to find this guy. He literally went to the FBI and tried to turn himself in. because he had his debt collectors coming after him, and at the time they just turned him away because they didn't have a case on him. But yeah, eventually he served his time and all that. But lottery, no. Okay, back to work here. How many 7-digit binary strings have an odd number of ones? How many 7-digit binary strings have an odd number of ones? Okay. So here we go. We have 7-digit binary. So we have 0. Okay. Have of ones. Okay. So we're going to say let A be, so we're going to assign A. Let A, let's see here, be the set of all 7 binary strings. Number of ones. Okay, so we need to know. Okay, so we need the cardinality of A. Okay, we're gonna break A into smaller parts. So we need to know odd number of ones. So we have a 7-digit string. So we have 3, 4, 5, 6, 7. So odd number of ones can be 1, 1. We can have 2. We have 3 ones. We can have 4, 5 ones. We can have 1, 2, 3, 5, 6, 7. And we could only have one of the last kind, right? Only one can have the last one. And of the first one, we can have 7. Because there's only one, you know, it can go through any one of these points. The rest would all have to be zeros. So we know that there's 7 of these. We know there's 1 of these. We got to figure out the rest. All right. Here we go. And so we're going to assign these. We're going to say this is let's say this is A sub 1, A sub 3, A sub 5, A sub 7. Okay? So the cardinality of A is equal to the cardinality of A sub 1 plus the cardinality of A sub 3 plus the cardinality of A sub 5 plus the cardinality of A sub 7, with the word cardinality, of course, being size, but we should all know that by now. All right. Now we must figure out the individual terms of the sum. Okay. So we know the first one, and we know the last one. I mean, those are like trivial to figure out. Just look at it, and then we know. So let's get the middle two then. All right. So we're gonna say 7, choose 3. Let's figure that out. And we need 7, choose 5 as well. And then we just add them all up and we good. So we know this is 7. We know this is 1. Just have to keep adding them. Okay, 7 choose 3 is equivalent to 7 factorial over 3 factorial with 7 minus 3 factorial. All right, and that comes out to 7 factorial over 3 factorial times 4 factorial, which comes out to 7, 6, 5 times 4 factorial over 6 times 4 factorial. Scratch the 4 factorials, and we can scratch the 6. So that's 35 on the first one. Okay. Now, how cool is that, right? See what I did there with the 3? Instead of writing it as 3 factorial, I just immediately rolled that into the 6. So if you, like I said, you memorize like the first I don't know, I would say 1 through 6 factorial. They're not hard to memorize. Sorry. So remember, 6 factorial, 720, and you know they start to get bigger after that. 7, I believe, is 540. Sorry. 1 second. Okay, so or 5040. 7 should be 5040. Okay, 720 times. Yeah. So, I have the in the back of my head the first 7 factorials on tap. So, you know, 7 factorial is 5040. 6 factorial is 720. 5 factorial is 120. 4, wait a minute. Yeah. Sorry. Sorry. Okay. Okay. I'm trying to clear my throat a little bit. Okay. Still sick. All right. I think I'm good now. Continuing on from where I left off. Let's finish this part. Okay. Let's get the 7, the last part now. We need, and this would finish off this section, and then I'll do the section questions in a separate video because I'm starting to lose my voice here. I want to keep coughing through the rest of it. Okay, so we have 7 choose 5. Okay, so 7 factorial over 5 factorial, 7 minus 5 factorial, 7 factorial over, alright, you know what? Let's do that. Yeah, we're going to say 7 times 6 times 5 factorial over 5 factorial times 2 factorial. So we have 7 times 6 times 5 factorial over, but we're going to scratch these. So we scratched off the, here we go. So this time, yeah, I scratched off the 5 factorial. And then we're going to have 7 times 6 over 2. We're going to have 7 times 3 now, which is equal to 21. Okay. Sorry. Okay, so now we have 7 plus 35 plus 21 plus 1. Okay, and that added up. Okay, 64. Anyway, sorry about the coughing fit. I will do the section exercises next time so I don't aggravate my throat any further. Hopefully you found this video both educational and entertaining. I will see you next time.